Right, so let's start. Today we are very happy to have Muni Zhou. Muni is a postdoctoral member at Princeton University and also here at the Institute. She got her Bachelor of Science degree in 2016 from Zhejiang University in China, and then moved to MIT for a PhD program in plasma physics. And today Muni will tell us about magnetogenesis and plasma dynamics.
Thank you for coming. I'm a new postdoc here. So today I would like to talk about something that I've been working on and I've been interested in working on in the future. And so any comments are welcome. So I work on problems related to magnetic fields in turbulent context. And so today I want to cover a couple of projects on these topics. So, but I might not be able to have time to reach the dissipation of magnetic fields, but I would like to talk about something about the genesis and the evolution of cosmic magnetic fields. So we know that magnetic fields is the universe, and for example, in this galaxy cluster, we can see the radio emission decays because magnetic fields in the galaxy cluster. And to make it more concrete, we look at it in the phase of the strength and length scale of the magnetic fields. So for a galaxy cluster, the magnetic fields usually have the strength microsource level and at the scale that's almost comparable to the system scale. If we go to smaller scales, we have more detailed observation. For example, this galaxy, you can see these small white arrows show the direction of the magnetic fields, and we can see the magnetic fields changes direction following the structure of this galaxy with these large coherent structures, and also with relatively large amplitude. And there are also intergalactic magnetic fields detected indirectly between the galaxy clusters. And we don't have a good measurement of such intergalactic magnetic fields, but there are different types of observational constraints that tells us the possible regimes in this parameter space for such galactic magnetic fields to exist. And so the main question we want to ask is, where are these magnetic fields from originally? So there are different paradigms thinking about this question. Some people believe that the magnetic fields are first formed within the galaxies and then dispersed and diluted throughout the cluster. And there are also another paradigm, which is the one I'm more interested in, suggests that the magnetic fields by first emerged as seed magnetic fields by different cosmic batteries and then amplified by the dynamo processes. So these two different conjectures are not contradictory, but we are going to focus more on the first one. So one way to form the first seed magnetic fields is through plasma instabilities. And the Weibel instability in particular is instability that can generate the first magnetic field from unmagnetized plasmas. So it can generate stronger magnetic fields, but only at the length scale of the plasma kinetics scales. And the only necessary condition is some anisotropy in the plasma distribution. So you can have an intuitive example of how the Weibel instability would work. So we can use two initially counter-streaming electron flows to present some anisotropy in the plasma distribution. It's basically two data functions velocity space. And in these counter-streaming flows, if we introduced electromagnetic perturbation propagating perpendicular to the initial flow, the particles will be deviated due to these perturbative magnetic fields. And this will form some local concentration of the flow and thus some current filaments at small scales. And these small scale current filaments will generate some feedback magnetic fields that happens to in the same direction as the original magnetic fields. And therefore this instability can grow. So the Weibel instability has been widely studied in the kinetic simulations, particle cell simulations, and also in laser experiments. It is widely observed on Earth. And it is a very generic instability with the only necessary condition being some anisotropy. So we think it should be ubiquitous in the intracrustal or intergalactic medium. And as long as we have some large-scale motions driven by gravity or have some thermal fluctuations, in principle, we should trigger this Weibel instability.
How does this tend to compete with other anisotropic instabilities, mirror instability, and so on?
So I think usually in the
Some magnetized, so there is no mirror instability.
I see. Sorry.
Sure. Right. So there are some other instability that are more competitive to Weibel. Maybe it's the two-stream instability, for example, in this context. And I think there are some study depending on how magnetized the system is and how relativistic the system is. There are different instability to dominate, but usually in the non-relativistic or magnetized case, the Weibel instability should dominate. Right. So, and it haven't been really studied. For example, if we just take a patch of the turbulence intercluster medium, how would the Weibel instability be triggered and generate the C fields? So, well, just to put this problem in the context of the history of the magnetic fields, so we are more interested in this Weibel instability generated C fields that occurs after ionization stage and then amplified by the plasma dynamos and then form the magnetic fields that we observe. So, we think including this microphysics of Weibel instability might enable us to think about a new pathway to generate magnetic fields. So presented as follows. So we could have the Weibel instability that generates C fields at the plasma kinetic scales, extremely small scales, but with relatively strong amplitude. And then such C field at small scale would have to migrate to large scales before it is dissipated. And in this case, it will grow in length scale and decay in its amplitude. And at some point, it might be picked up by the turbulent dynamo and be amplified to become the fields that we observed today. So one important question in this conjecture is that what would be the seed magnetic fields that is self-consistently produced by the large-scale turbulent flows or large-scale turbulence that we have. And
what is the white area in this plot? Is it like not measured in any observations?
Which areas?
The difference between the gray and the white areas?
The white areas.
This plot.
This is, so the gray areas are the areas that are blocked out by constraints. This white areas is the relevant areas for intergalactic magnetic fields.
So in that picture, you never need Biermann battery.
Well, Biermann battery is an alternative explanation. It's not contradictory to this one. Or maybe it's a good question that whether Biermann battery or the Weibel would dominate. And the Biermann battery has its own problem that it generates C fields at large scales, but with weak amplitude, and is saying that it hasn't been proved that the dynamo would be able to amplify such C fields within a relative to time scale to the observed field. So I think different.
Is he saying you end up in the white region to the right rather than up there with the galaxy?
Right, it might be around here that it has the right scale, but the amplitude is too low. And for this Weibel path, the amplitude is large, but the scale is too small. So there are two different problems to be solved. So the first part of this presentation, I would like to focus on the first step, talk about the Weibel C fields. In particular, I want to understand how the Weibel C fields generated from generic motion of unmagnetized plasma, and what would be the differential topology of such C fields. And for the second part, we want to study the long-term evolution of such C fields. I want to understand if such C fields could grow to sufficiently large scales and be amplified by the dynamo. So let's start with the first part about how the Weibel C fields could be generated. So let's just do a simple thought experiment. Like in a turbulent, in a large-scale turbulence, we can take a small element, a small 3D box, and here we will have a trivial initial condition of uniform Maxwellian plasma without any electromagnetic fields in the beginning, and we can stay in the sub-relativistic regime. And so at such small scales, any large-scale cosmic scale motion is effectively a shear flow, or maybe a compression, but we can only focus on the shear flow for now. So in such 3D box with simple plasma, we can apply a constant system scale shear force that is in the y direction and has its variation in the x direction, shown like this. And initially, if we don't consider electromagnetic fields, this is a simple system where the only external force is this, the only force is this external shear force. And so this is a simple system that we can actually find the exact analytical solution. And the solution looks like this. So this is plot of distribution function in the velocity space at the location with the maximum shear. So initially we have this Maxwellian distribution. And as the system starts to be driven by the shear force, we can see the distribution start to be distorted, deviated from initial Maxwellian, and eventually have this complicated structure in velocity space with things at small scales and indicate this signature of phase mixing. And in such a system, we know that it is because we have the transport of this non-uniform Y momentum in the x direction through free streaming. So the phase mixing could occur, and in principle, this could give rise to the pressure anisotropy of the plasma, and therefore the free energy could build up in the plasma. And then we can, with this analytical solution, we can do more calculation. For example, we can actually calculate the evolution of the pressure anisotropy at a short time scale limit, and the pressure anisotropy should evolve in this thermal crossing time scale, which is a slow time scale. And then if we consider only at small time scale limit, we can consider only the electron instability or equivalently consider pair plasma. And using our exact solution of exact unmagnetized solution, we can calculate the linear dispersion relation of the Weibel instability. And we found out the dependence of the most unstable wave on the pressure anisotropy and the corresponding growth rate of magnetic fields on the pressure anisotropy. And because we know there is a symptotic timescale separation exists in such a system, the growth of the Weibel instability is a kinetic instability, so the growth rate of it is much larger than the evolution of the background equilibrium, which is also the evolution of the pressure anisotropy here. And with this timescale separation, we can integrate the equation and obtain the time evolution of the magnetic energy represented by the plasma beta here. And we can see because the anisotropy equilibrium is also evolving, this is in fact a super exponential growth. In this type of instability, we know that when the argument of this exponential reaches order unity, it reaches the end of the linear stage. And hereafter, the nonlinear effect becomes important. And at the end of this linear phase, we can also find out how the length scale of the Weibel fields would depend on the pressure anisotropy and therefore on the other parameters of scale separation and this normalized acceleration of representing the shear rate. And we also know that the Weibel instability should saturate when the plasma become magnetized, meaning that when the lumbar radius of the particles become comparable to the scale of the field itself. And using this criterion, we can find out the scale dependence of the saturated magnetic energy presented by inverse beta on these two important parameters. So sorry for this long algebra, but this is the main deliverable of our theory, that we found out the scale independence of the length scale and strength of the saturated Weibel C fields on these two key parameters. One is the shear rate, or similarly the Mach number of the system, and the other is the scale separation between the microscopic and the macroscopic dynamics. And then we can proceed to test our theory using some particle in cell simulations. So here I'm going to show some numerical results using the code Zhou, basically just simulating the exact situation, scenario that we just described. So we have a 3D box with initially unmagnetized Maxwellian plasma, and we are going to add a constant shear force on this box. Then this animation will show the evolution of the magnetic field strength. You can see that once we start to push this box, push the particles in this box, you can see the clear formation of the Weibel filaments at location with maximum shear. And then there is a long nonlinear evolution, and eventually we can see the formation of some clear filaments at a saturated state and at the direction of this shear force.
So the setup here is just sinusoidal like forcing, like some external sinusoidal forcing.
Right, it's just a constant forcing to push the particles. The force has a shear form.
So forcing is not time dependent.
No, it's constant. And so this is basically how the system looks like. So when you actually push a magnetized plasma, there's something interesting happening instead, rather than the plasma just being pushed around. And we want to understand this system in more details. So to be more quantitative, let's first define three important quantities that characterize the energetics of such system. First is delta anisotropy that present the free energy of the thermal in the thermal pressure anisotropy. And then this Mach number square, which present the bulk kinetic energy, and the inverse beta that present the magnetic energy. And they are all normalized to the total thermal pressure by the definition. And so once the system is driven by the shear force, we can see that all these three quantities start to grow. The shear force will drive the bulk flow and thus the increase of the Mach number square. And with the presence of this shear force, shear flow, the pressure anisotropy will develop due to phase mixing. And once the pressure anisotropy is developed, the Weibel instability will be triggered, and this will cause the increase of magnetic fields. So what we are going to do is we are going to divide this whole evolution into a few distinct stages, and then we are going to qualitatively describe what is going on in each stage.
How well do you know the shear rate? Does it come from the simulations? Is there any indication of what you should put for the force, or is it just is the simulation insensitive enough to
So we are interested in the case that when to see the generation of magnetic fields in that phase, it's basically controlled by the force that we can create the solution, and we know how the development of flow, the shear flow would depend on the force that we apply. It's controllable.
But in the initial galactic problem, do you have some idea of what the realistic parameter for that is? Or is it just like you just try out some numbers and then roughly you pin down which regime this is?
I think we roughly know the Mach number of such systems, and we know the velocity and we know the length scale. So we roughly know the shear rate is about 0.1 or 0.2. So.
And what about the profile of shear? It looked like you had a sort of sinusoidal profile.
Right.
Is that correct?
It is artificial.
No, I understand. Yeah, but I mean, like whatever. It looked like it was sinusoidal. What if it's just a linear shear?
Yeah, I say artificial because, of course, it's a linear shear will be a better approximation if you look at any shear at small scales. And we artificially do sinusoidal just because we have periodic boundary conditions of our simulation, and that is easier.
Can't you use something like shearing boxes to still use linear shear?
That would be a better way to do it. I agree, but I think that
like locally in any situation in astrophysics, you expect shear to be linear, right?
But yes, you're right. That is the better way to do it. But the result shouldn't change that much, because in our case, most things, interesting things happen at a place with maximum shear, at this largest gradient of the shear, and we are basically losing some scale separation because we use this sinusoidal profile. But indeed, in numerically linear shear flow will be better.
You're adding an actual force to the particles to push them.
Right.
And that's different than an initial condition in which there was bulk motion in the plasma that would then phase mix and stop plasma. I mean, does that affect the Weibel? If you just started from a box which had an initial shear profile imposed but no force on it, would you still see Weibel and application of the field in the same way?
I would assume so. And the way we drive this is just to trying to mimic a development of a shear flow. And
is that because Weibel grows faster than the viscous
exactly, because
breaking of the shear layer?
Because we have this time scale separation, the growth rate of Weibel is much faster than any of the change of the background equilibrium, the shear flow rate. So it shouldn't be a problem. And I will start to describe different stages. So initially, our plasma is unmagnetized and driven by this shear flow. And in this case, we can find a physical solution represented by the dotted line here. And we can see that indeed, at least in this initial stage, the development of the pressure anisotropy and the flow agrees quite well with the solution. And then once the pressure anisotropy is developed, the Weibel instability is triggered, and then this causes the growth of the Weibel magnetic fields. And then first we enter this linear Weibel stage, where we can see the exponential growth of magnetic energy presented by this inverse beta here. And this is the stage where we see the clear formation of these Weibel filaments at the place we have large shear. And then the linear stage this instability quickly reaches the end of the linear stage, where we can see the pressure anisotropy reaches its maximum value. and also the growth rate of the magnetic field, which is represented by this magenta line here. This is basically a derivative of this blue curve, the evolution of magnetic energy. So this is the end of the linear stage, and after that, the nonlinear effects will start to matter, and this will cause the free energy will start, the depletion of the free energy by the instability will be faster than the supplement of the free energy by the force, and then we will see the decrease of the pressure anisotropy, the free energy in this case. And when we enter this nonlinear phase, we can see that the pressure anisotropy decreases and the magnetic growth rate also decreases. The field at this point becomes strong enough to change the trajectory of the particles, change the overall dynamics of the system. And indeed, at this point, the depletion of the free energy becomes much faster than the depletion of the free energy by the force. And then soon after, the instability reaches the situation when the plasma becomes magnetized. And in this case, we can see it from the spectrum here, where this blue curve shows the magnetic spectrum, and this dotted dashed curve shows the probability distribution function of the Lama radius of the particles. And in this stage, when the instability saturates, we can see a sufficient fraction of the particles have their Lama, with their Lama radius being smaller than the characteristic length scale of the magnetic fields, meaning that they are being magnetized. So this is indirect evidence saying that the magnetization is the condition for the situation of the instability. And after that, we enter a long-term nonlinear evolution of these Weibel filaments after it saturates. And during this stage, we can see the scale of the filaments move to the large scales, to the box scales, and the magnetic energy start to pile up at the system scale. So I'm going to skip we did do some parameter scan of such problem, trying to confirm our theory. And so I'm going to skip those quantitative analysis and just present our summary. So indeed, we found out that the collisionless plasma can be spontaneously magnetized by a large-scale motion, as simple as a shear flow. This is through the instability, because we started with unmagnetized plasma, and we just simply apply a shear force that causes a large-scale shear motion, and we found out the instability will magnetize the plasma. And we also found out the scale dependence of the strength and the length scale of the Weibel C fields on two key parameters: the scale separation between the microscopic and macroscopic scales, and the shear rate or the Mach number of the system. And then this is the main deliverable of this study, and we can try to put it to some use by doing some estimation. For example, if in the hot and dilute intercluster medium, we know the system scale is about 10 kiloparsec injection scale, and then the electron spin depth is about 10 to the minus 12 parsec. And this relation tells us that the Weibel instability should cause the plasma beta to saturate at 10 to the 8. And this will correspond to a 0.1 nanogauss magnetic fields at a scale of 10 to the 4 spin depth. So this is much larger than the Biermann fields, which is the main competitive alternative of the Weibel fields, as it was mentioned. But the fields is at much smaller scales. So whether the fields could be interact with a dynamo is not the main question. But indeed, this study tells us that the Weibel seeding could be a possible way to seed the turbulent dynamo. And inclusion of this microphysics is important when we study this large-scale turbulent motion. And then, so well, we are trying to understand what will happen to this. What is the long-term evolution of such Weibel C fields? What will happen to it afterwards if you could interact with the large-scale flow, etc. So, and in this animation, we show the animation of magnetic field strength, and the setup is exactly the same as the previous one. And the only difference is we evolve this system for a longer time and see what will happen. So similarly, we see the formation of the filaments due to the shear force, and then the saturation of the Weibel C fields, and then the system enters this prolonged nonlinear evolution, and we can see the filaments become aligned with the force, and they start to merge and grow into larger scales. So, and this bring us to the second stage of this whole picture that we want to understand. That is, the filaments seems to be doing the coalescence and trying to grow into larger scales. So we want to understand this process, that when the filaments start to coalesce and migrate to larger scales when energy is decaying, what exactly is the trajectory of this part, and if you will be able to preserve enough energy at a large scale. So the saturated C fields can be represented by these typical magnetic flux tube structures, where they have these helical magnetic fields and with a strong axial component. And I also want to mention that such magnetic flux tube is not unique to this type of Weibel instability, Weibel C fields. It is actually detected in various environments, especially in the solar system. For example, in the Earth magnetosphere, when we have this large-scale magnetic reconnection, it will leave a group of small-scale magnetic island or magnetic flux tubes. And the long-term evolution of such magnetic flux tubes is still unknown, and the role of it in determining the turbulence in that region is also unknown. And in the solar wind, this flux tube or flux rope structures has been widely detected. And when the solar wind propagates from the sun towards a further area, the decrease of the number of flux tubes and the decrease of energy and the increase of length scale actually goes beyond the natural adiabatic expansion. So we still don't know what is the dynamics of the flux ropes in the context of solar wind. And also such flux ropes are detected in solar corona, and it is believed to be responsible to the robust energy dissipation and particle heating in that area. So in all this context, the system evolution is to a large extent dictated by the interaction of the flux tube in a turbulent environment. And it's necessary for us to develop description to describe the dynamics of a large number of such magnetic flux tubes. So here I'm going to present a very simple minimum analytical model for such case. So let's first consider a system with a strong background magnetic field for simplicity. So at this point, it might be a bit irrelevant to the initial magnetogenesis problem. We have no initial magnetic field. But first, this is for simplicity, and also because the final saturated C fields we saw have a strong component of magnetic field that is parallel to the flux tube itself. So maybe there is some maybe it is valid to some extent to assume a background magnetic field. And so in such a system, we also assume we have volume filling flux tubes aligned with this background magnetic field with alternating polarities. And for each single flux tube, it has helical magnetic fields that can be decomposed into an axial component that will give rise to the axial magnetic flux, and also a perpendicular component that will give us the poloidal magnetic flux. And the length scale, the length or the radius of the flux tube will be defined by the correlation length of the magnetic fields in these two directions. So we know that when two flux tubes with the same polarity with the parallel current approach each other, they will be unstable to the coalescence instability, and they will merge into a larger one by reconnecting their poloidal flux. And this is one basic process of the interaction of the magnetic flux tubes. So based on this, we can develop a very simple minimum model to describe a large ensemble of such flux tubes. So we assume that we have a sum of identical flux tubes, and they will merge in this hierarchical fashion through the coalescence instability. And we assume that they will merge in discrete time steps, and that therefore each generation can be denoted by an index here. And we also assume they merge in pairs. And then we can talk more about a single merging event. So when flux tube merge, the physical quantities will start to evolve, and this merging process should follow some conservation laws. So for example, on the perpendicular plane, each flux tube can be characterized by its magnetic potential, which is basically the 2D poloidal flux defined by the perpendicular magnetic field multiplied by the perpendicular length scale. And also they have an axial flux that is given by the guide field. So when two flux tubes merge, they should follow some conservation laws. So first is the conservation of the axial flux. The axial flux should add when two flux tubes merge, and because the background field is a constant, the cross-section area should be conserved. And therefore we know that the perpendicular length scale of the field should increase by a factor of square root of 2 through its merger. And the magnetic potential should remain during this reconnection process, and therefore the strength of the perpendicular magnetic field should decrease by a factor of square root of 2. And this is what happened on the perpendicular plane. And the perpendicular dynamics should be related to the parallel dynamics with a certain causality, which is known as the critical balance.
This is assuming that you have two identical things that are merging, rather than one big and one small.
This is assuming two identical things. And you are right that there are also some other extreme cases, one big one interacting with one small one. And if how you will affect the dynamics, we can talk about.
So you start off with all the small ones merging, and then the next layer, all the slightly bigger ones merging, and so on and so on.
Right. So if you think about the spectrum, we also think that all these flux tube at a certain time can be presented by a certain kind of delta function. And this is basically a version of a delta function.
So why does critical balance apply here?
Because it is a dynamics of magnetic fields in the turbulent system, and it is related to the magnetic field still is correlated in different directions, and you would assume the dynamics in one direction should correlate to the other one.
But can you be in sort of weak turbulence regime?
Can that be a weak turbulence regime? Well, if you are in a strongly magnetized system, you are turbulent enough. In reality, if there are some realistic system that is in a weak turbulence regime, is that a question?
I think the argument for critical balance in turbulent systems is that if your turbulence is in a weak regime, the system will evolve towards a strong regime. And I'm not sure if the same argument can be made about the flux-felt merge.
It's a good question. If I start with a weak turbulence regime, I don't know. I think it's motivated by the fact that most of such realistic system is actually in a strong turbulence regime.
What would weak turbulence and strong? What would that mean in this context?
What the turbulence means for me, it means that the things should satisfy critical balance. That, for example, if you take a patch in a solar wind, when you have the strong turbulence and it's actually composed of such flux tubes, I would imagine the dynamics should follow critical balance.
What that is? What's critical balance?
It means that the dynamics in the parallel and in different directions of the turbulent system should follow certain causality, that the time scale should match. And in this context, for example, in this context, I would explain it in this way. So when flux tubes are merging and moving around on a perpendicular plane, there is associated perpendicular, there are different associated perpendicular time scale for different dynamics. And the fastest one for it is the eddy turnover time of such flux tubes on a perpendicular plane. And when within one eddy turnover time, within one nonlinear correlation time on a perpendicular plane, the alpha waves is also propagating in the parallel direction. And you can imagine that within one correlation time, that the parallel signal is also correlated. But once your eddies become decorrelated on a perpendicular plane, you also lose this correlation in the parallel direction. And this is basically the idea of critical balance, that the perpendicular and the parallel dynamics should satisfy some causality. They would occur at the same time scale.
So in a weak turbulence, you would get lots of eddy turnover times before this decorrelation happens.
Yeah, so in this context, if we believe it's a strong turbulence regime and satisfy critical balance, the perpendicular time scale, which is determined by this eddy turnover time, should balance the parallel time scale, which is determined by this propagating of the information through alpha waves. And then balancing these two time scale basically tells us that within one merger, one perpendicular dynamics, the length of the flux tube should also increase by a factor of 2 in such case. And so all of this, after all this is still a reconnection process, and the merger process is essentially a magnetic reconnection of the colloidal flux. So we should think about some reconnection details of such event. So if it's in the MHD regime, the Lundquist number, which is the parameter that determines the reconnection regime, defined by the length scale multiplied by the pervading magnetic fields, or the velocity divided by resistivity, is proportional to the magnetic potential, which is a perceived quantity through this process. And if it's in a low Lundquist number regime, the reconnection rate is proportional to the Lindquist number to the 1/2, which is a perceived quantity. And if it's either in the high Lindquist number MHD regime, or if it's in the collisionless regime, the Lindquist rate, the magnetic reconnection rate is constant. And therefore, we think that whatever regime we start with such flux tubes, the magnetic reconnection rate should remain a constant. And this tells us that the merging process should remain in the same reconnection regime in which it starts initially. And within this assumption or condition that we argued, we can calculate the timescale of each generation, which is determined by the reconnection timescale, presented by the length scale divided by the reconnection rate. And the reconnection rate is related to magnetic field through the reconnection velocity is related to the alpha reconnection rate. And therefore, we know the evolution of timescale through each generation. And by combining this recursive relation of the timescale with the previous ones, we can derive the continuous time description of these quantities we want to know. For example, the perpendicular wave number corresponding to the length scale decreases t to the minus 1/2, and the perpendicular magnetic field decreases t to the minus 1, meaning that the magnetic energy decreases as t to the minus 1, and the number density of this flux tube decreases t to the minus 1. And all of this happens at the reconnection timescale. And so this is the main deliverables of all this toy model. And in retrospect, we know that we don't have to go through all this toy model. So we can just derive a simple formal scaling theory based on the argument we use. For example, we know that in this such a system, that characteristic timescale is the reconnection timescale with a constant reconnection rate throughout the whole evolution. And if you want to look at the decay of the magnetic fields, you will the relevant timescale, as we said, would be the reconnection timescale, and find out the form of this decay. And then during this decaying process, some conservation laws needs to be satisfied, which here is the conservation of the colloidal flux. And just by combining this conservation law with the decay of fields, we can quickly find out that the energy should decay at t to the minus 1, and the length scale should grow at t to the 1/2, and it should all occur at the reconnection timescale. And also the parallel dynamics should follow the critical balance and increase as t to the increase linearly with time, as we described. So this decay law is not new, that this t to the minus 1 energy decay has been derived by this kind of decays ago. And what is new here is that we argue that the system should decay at the reconnection timescale, as opposed to the aphanic timescale, which is previously believed by the typical MHD theory, at least in this magnetically dominated regime. And therefore, in this magnetically dominated regime, the system should decay at a much slower timescale than we would previously believe.
So you're basically saying that previous studies did not take plasmoid formation into account.
So
Is it plasmoid formation that makes the difference here? Because you say that you go to constant reconnection rate compared to previous studies.
Not exactly. So what I'm trying to argue here is that there are different regimes of decaying turbulence. And in a specific case, when it's magnetically dominated, where the overall dynamics of the system is controlled by this merging of flux tube of magnetic structures, the decay of the system should be much slower than the equipartition aphanic turbulence. And the constant reconnection rate is that we mentioned here is just saying that if we believe in this simple model that when the fields growing from small scale to large scale through merger, the reconnection rate, the reconnection regime for this should be in the same regime and therefore has the same reconnection rate. Because it might be the case that initially when you start with some kinetic scale C fields and then you grow to large scale MHD scale, the reconnection could change the regime. But we are trying to argue that because of the conservation of the colloidal flux and how the merge happens, it should remain in the same regime that you started initially. That's the question.
All right, it might sound silly, but then what's the role of these alphanic waves? Because it time scales much faster. So you're saying that there's some mechanism keeping the evolution of the decay of the system slow.
Right. I think it's the reconnection that keeps the keeps it slower. Well, it also depends on reconnection regime. If it's in a collisionless regime with a larger reconnection rate, this should also happen faster than MHD regime. But we are saying that is that the alpha wave is always propagating in the system, but the decay of energy or the time scale for the evolution of such system is actually set by reconnection as opposed to the propagation of alpha waves. Then we can have so we found out that quantities evolved in a power law manner is indicate some self-similarity of the system. And in fact, for example, this decrease of power decrease of wave number and magnetic energy can be represented in a different way. That quantities we can simultaneously rescale different quantities using a scaling factor that is determined by the two arbitrary chosen moments of time. So basically, the power law evolution can be represented equivalently in this rescaling of the quantities. And this is also consistent with the generic rescaling symmetry of the MHD equations. And with such rescaling symmetries, we can quickly derive some interesting properties, for example, for the magnetic spectrum. So we know that with such a rescaling symmetry, the magnetic spectrum should satisfy such self-similar evolution that it can be written as a t to the power law of t multiplied by a scaling function or power law of t multiplied by a scaling function. And here, these two power laws is determined by the physics of merger through reconnection. And this scaling function is determined by some energy distribution of in the system that we don't know yet. But we know that in a turbulent system, usually the scaling function follows also a power law. And if we use this assumption, we can know that the magnetic spectrum could, in principle, be written by a power law of t multiplied by a power law of k, with the power law indices related in this way, if the system indeed evolves in a self-similar way, followed by this successive merger. And this is just another small prediction based on the self-similar properties that we can confirm later or check later. And then we can perform some direct numerical simulations to test what we have just described. So we are going to perform a 3D reduced MHD simulations. So in this type of equations to simulate the scenario that we just described. So we started with a system with a checker box of magnetic flux tubes with alternating polarities. And then we give this system a small perturbation and let it evolve at a free decay. So this animation will show the evolution of the current sheets, meaning the place with strong current. And so initially there is no current sheets, and once the tubes start to merge, we can see the development of current sheets. And then because initially the box is too long to maintain the causality, so the flux tube initially break and twist in z direction, and that caused the initial phase of developing turbulence. And then afterwards, we see a clean phase of decaying turbulence, which is dominated by the merger of the structures and the development of these progressively large structures. And then we can look at the system more quantitatively. So we see a two-stage evolution of the system. First is the development turbulence stage, because due to the breaking of the system, trying to reach to a critically balanced stage. And in this stage, this plot shows the time evolution of the kinetic and magnetic energy. You can see in the development turbulence stage, we have the robust dissipation of magnetic energy and quick increase of kinetic energy. And then when we enter the second decaying turbulence stage, we see this clean t to the -1 decay law that is predicted by this. This is the stage that all the previous model is trying to describe. And we can also look at the number of structures of the system. In the developing turbulent stage, indeed, we see the increasing number of structures corresponding to the increasing complexity. And during the decaying turbulent stage, we see a t to the -1 decay law also predicted by the toy model. And we can also calculate the time evolution of the energy integral scale for representing the characteristic perpendicular length scale. And indeed, in this decaying turbulent stage, we see a t to the 1/2 increasing of the correlations. And so we could also try to characterize the geometry of each flux tubes by calculating the structure function of such flux tubes. And so we calculate the structure function of the structure flux tubes throughout the generation. It's represented by this dotted, these blue dots here. And we can see that as the flux tube growing from small scales to large scale, the increase of its length scale, perpendicular and parallel length scale, basically follow this critical balance criterion, meaning that as the flux tube merge and expand, the aspect ratio is controlled by this critical balance criterion until the later stage. And then we can also look at the time evolution of the magnetic spectrum. Initially, the magnetic spectrum is this blue delta function at the cross-section of the initial flux tubes. And then during the developed turbulent stage, we can see a k to the -2 magnetic spectrum dominated by this sharp magnetic reversal at the place with current sheets, basically a Berger spectrum, which is quite ubiquitous when people simulating shocks, etc. And then at the decay turbulent stage, we see a typical -3/2 turbulent cascading spectrum. And indeed, if you look at the time evolution of the spectrum, of the peak of the spectrum, or the time evolution of the spectrum at a fixed wave number, the measured index indeed satisfied this relation that we predict based on the self-similarity. So this basically confirms that indeed the system evolves in a self-similar way from small scale to large scales. And so we think that the scenario that we described there, that the evolution of the field from small to large scale is more general than this unique magnetic flux tubes. And indeed, if we initialize the system with small scale random C fields, in the case both with strong guide field and without strong guide field, we see a similar behavior that the large scale magnetic fields will emerge from initial small scale fields, and the measured evolution of the quantities like the decay of energy and the growth of length scale indeed follows our prediction. So just the bottom line of this is indeed that if we are in the magnetically dominated regime of the turbulence, the evolution of magnetic fields is dictated by this merger of magnetic structures. And this is the basic process to help us generate large-scale magnetic fields. And also want to mention that there's another nice paper by Hosp and Shikutian that developed a formal theory based on a new invariant that they discovered to formally describe the evolution of such system, as opposed to a toy model that we just described. And so, as Chris just mentioned, what if you have a large tube merged with a small tube? What if you have a complicated distribution of the flux tube instead of an identical one? So I just want to quickly mention the other work that we did. In this case, we're trying to address the question of whether the system evolution that we predicted here will change a lot if we have a non-trivial distribution. And in that work, we derived such a Fokker-Planck type of kinetic equation of the plasmas, where the of the magnetic fields, where the magnetic flux tubes are described by a distribution function over their characteristic properties. And then in this case, the merger of the flux tube is implemented through a collisional integral of such a system and governed by the reconnection physics. And the conclusion of such study is that even if you have a quite non-trivial distribution, the system evolution remains similar to the one with identical flux tubes, because it is still the evolution is still dominated by the likewise merging. Right, and then
is there any theoretical similarity between these merger of the tubes and the inverse cascade of 2D turbulence? Impressions that like in 2D, right, you can form larger eddies from small eddies, and whether is there any similarity?
Right. So the inverse cascade of 2D MHD turbulence is already quite well studied, and it is thought as governed by the conservation of the magnetic potential square, which is invariant in the 2D MHD equations. And it is also believed that in 3D, the inverse cascade of magnetic fields should be governed by the magnetic helicity, which is the integral of potential dot magnetic field. And so these are well studied. And so one relevance of our study to this inverse cascade business is that this part that I skipped, that a few years ago, there is some very intriguing numerical discovery of the inverse cascade of magnetic fields in a non-helical system, meaning a system with zero net magnetic helicity. And this is a bit surprising because previously all this inverse cascade is explained by the conservation of helicity. But in the work that we just described, the system overall have zero net helicity, and indeed we see this inverse cascade. So we will trying to make the point that magnetic reconnection is the underlying physics in the case where we have zero magnetic helicity that could still lead to the inverse cascade. And so for a more formal argument, I will refer you to this paper that they discovered basically the self-similarity invariant instead of magnetic helicity that described the inverse cascade in such non-zero helicity case. Right, and this is the summary of my presentation. So overall, we are trying to propose a possible way to see the plasma dynamos that is composed of these few main steps. And so the first part of the talk, we are describing some physics in the first step, that how the Weibel C-fields can be produced by generic large-scale plasma motion and spontaneously magnetize the plasma. And for the second part of the presentation, we are trying to talk about something in the second stage, that how the inverse transfer of magnetic field can be achieved by the coalescence of magnetic structures through magnetic reconnection. And there are a lot to do in order to have a full understanding of this trajectory. But if anyone is more interested or have some knowledge to share about the observation or anything, you can always talk.
So it looks like in this, I mean, the second part and the first part are connected. You produce these filaments in the first part, and then you try to merge them in the second part. The first part, you get to the field strengths of 10 to the minus 10 Gauss. Now, as you start merging to the scales which become interesting, and your field strengths is going to decay, as you showed in the second part of the talk, would you not fall below the Biermann battery level?
So to quantitative answer this question, there's a lot to do. There are still many gaps in all of this. So I think you're asking.
Like if you take the scale, you know, the initial scale of these filaments propagated to whatever is interesting, and you have scalings for, well, basically how your field will be decaying with, you know, with the scale, right?
Right.
So if you just naively plug this in, what field dilution would you get? Is it always 1 over the scale, the field strengths, if that?
So first, what we have talked about this Weibel fields is only electron Weibel fields, and we have only doing a pair plasma study. In fact, ion fields would be much stronger, could be much stronger than the electron fields. That is to be studied. And if we just take the electron Weibel fields and let it dilute when it grows to larger scales, I think when you reach the larger scale, it will be weaker than the Biermann battery field. That is the estimation. But the hope is that it doesn't have to reach to all these large scales before it is picked up by the turbulent dynamo. So another question to study is at which point when that the turbulent dynamo would take over the nonlinear evolution of the C fields and start to amplify the fields. So with the hope that the dynamo could operate at small scales, then the Biermann field, that the Weibel field could be a possible way other than the Biermann battery field.
What is the physical parameter determining where at which scale the turbulence dynamo will pick up this? I mean, why it does not pick up it at very small scales? That seems to be a typical scale.
That is a great question, and so I think the simple answer is I don't know. Naively, I would think that it is at a scale where the magnetic energy becomes comparable to the kinetic energy of the flow that dynamo will start to react to C fields. But that is probably also not the case for this dynamo study. I think it's a complicated question given also by the complicated geometry of the C fields. So how does flux tube type of C field would entangle in the turbulent environment and then become the fold structures and then interact with the flow? I think they are all unknown questions to be studied. They are good questions.
I just also had a technical question about, you mentioned about the decay time scale. Like the Alphen wave scale, time scale, and these reconnection scale, and you said this is much slower. But then you said the decay is some power law dependence, right? I guess power law decay does not have a scale.
So what do you mean by power law decay has a scale?
I mean, you said the decay is something like proportional to t to -1.
Right.
And then I mean, there's no parameter for determining the time scale for these kind of.
Also the T is, sorry, the T is the normalized T that is
Oh.
normalized, depends on if you normalize to R potential.
Oh, but even if you normalize it, I mean, still after that, you have the same function form, right? Because it's.
Yes, the polar indexes is the same whether which depending on the truth theory of which time scale it is decaying on, but the index is the same.
Yeah. Okay, we can talk about that later. Yeah.
This plot is at a particular redshift, I guess. This plot is at a particular redshift.
So we are thinking of a redshift about 10 that is after the realization. When the plasma is the typical collisionist plasma that we are familiar with and affected by all the radiative tracks. But I don't know how to, maybe there's a way to generate to the earlier times, but that will need more work.
You translate like the other bounds like CMB or something to that direction.
I think that would be interesting, but we'll have to take into account the other physics that happens around that area of the time.
Any more questions? But let's thank Muni again.